Today we're going to look at three interesting proofs of the Pythagorean theorem. This is a theorem that's been proved hundreds, probably maybe thousands of times in history. And we're going to look at three proofs in particular because they're theoretically interesting and they're useful in education. So the first proof is based on a triangle similarity argument, and it's right here in front of us. We have a length A, a length B, and a length C here unlabeled. That's the length of the segment AB here. In this right triangle, of course, ABC. So if we drop the altitude from C to the opposite side, then we get three similar triangles. We have the triangle ADC, the triangle BDC, CDB, and the triangle ACB. And these are all similar. And so we get equalities of ratios. In particular, the short side over the hypotenuse of CDB, A over its short side, A over Z, is equal to the hypotenuse x plus z over a, because that's the hypotenuse divided by the short side in the larger triangle. And so that gives us this equality of ratios, which if we cross multiply gives us a squared equals xc plus z squared. If we compare the long side to instead the hypotenuse, then we can see that the hypotenuse b over the long side x in this triangle ACD agrees with the hypotenuse x plus z divided by the long side b in this triangle ABC. And so that gives us this equality of ratios, which if we cross multiply gives us b squared equals x squared plus xc. Now it's simply a matter of adding these equations. A squared plus b squared equals x squared plus 2xc plus z squared. Now if we factor this, that's x plus z quantity squared, which is exactly c squared. And that completes a proof of the Pythagorean theorem. So that's our first proof. It's quite simple and short. Let's look at the next proof. The next proof is kind of a pinwheel pattern. The triangle ABC is placed within a square with side length C and together with three more copies of itself. So this triangle BEH, this one EGD, this triangle DFA, these are all four congruent right triangles. And then that leaves us with a square in the middle. What's the size of this square? Well, this side length here, CB, is A, and this side length here, HB, is B. And so that makes this side length A minus B, assuming that A is the longer side. So how does this help us with anything? Well, we have this exterior square here, and its area can be computed in two completely different ways. First of all, it is made up of 5 parts, 4 triangles and 1 square. And so we have 4 times the area formula for the triangle, which is 1/2 base height, plus, and then we're going to add the area of the square, A minus B quantity squared. So when we add all this up and when we multiply this out and simplify it, we get a squared plus b squared. Because this thing multiplies out to give you a squared minus 2ab plus b squared, and then this cancels the 2ab. But there's another way to calculate the area of this exterior square, and that is to simply take its side length and then square it. So that's c squared. So the area of this entire square can be computed on the one hand to be a squared plus b squared, and on the other hand can be computed to be c squared. If both of these calculations are correct, and they are, then a squared plus b squared and c squared must be the same answer. And so we get the equation a squared plus b squared equals c squared for the right triangle. So that's the second proof. The third proof is due to Euclid. At least it appears in Euclid. I think it's due to Euclid. And it's a little bit harder to visualize, but it's an important proof here. So this strategy is based on understanding a squared and b squared. I guess this is a squared and b squared and c squared in terms of literal squares. So if this side length BC is the quantity a, then this square's area is the most literal interpretation we could have for a squared. And this square's area is b squared, and this square's area is c squared. So the goal then is to prove that this square, together with this square, has the same amount of area as this larger square here. Now the strategy is to drop a perpendicular from C to AB and continue it so that it cuts across this square. So it meets at points K and J along this square. And we have 2 interesting triangles here in red, the triangle CAD and the triangle GAB. So these triangles are congruent. Let's think about why. The value CA agrees with the value GA because they're both part of this square here. The value AB agrees with AD because they're both part of this square. So that's two sides. We also have an equality of the anterior angle because this angle CAD is 90 degrees plus this unknown. And the angle GAB is also 90 degrees plus the very same unknown. And so the angle GAB agrees with the angle CAD. The side CA agrees with GA. And the side AD agrees with AB. So we get side angle side for the two red triangles, and that makes them congruent. If they're congruent, they have the same area, and that's what's noted here. Area AGB equals area ADC. Remember, the parenthesis notation means the area of that triangle. But AGB is exactly half of this square. It doesn't look like it because it's not contained within the square, but the area of AGB is 1/2 the base times the height. And the height of this triangle relative to this base is exactly the perpendicular distance from B to the extended line GA, which, because everything is parallel and perpendicular here, is exactly the distance CA. So in other words, this red triangle, GAB, has an area 1/2 its base times its height. And therefore, it is exactly 1/2 of the area of this square. This other red triangle, we can think of its base as being AD, in which case its height is this distance DJ, which is the perpendicular distance from its third vertex to that line. That makes this triangle ADC have an area which is exactly half of the rectangle AKJD. So what we get from the congruence of these red triangles is half the area of this square is half the area of this rectangle, ADJK. Well, if half of each is equal, then they must be equal. So in other words, this square has the same area as this rectangle, ADJK. So now we just have to do the exact same argument on the other side, but the argument is subtle enough that we might as well repeat it carefully. So let's look next at these blue triangles, this one and this one. So the triangle ABI is congruent to the triangle HBC. Let's think about why. HB agrees with AB because they're both part of the same square, ABHD. So AB and HB are the same in length. BI and BC are the same in length. And the angles that each of these triangles makes at B are equal. This angle is 90 degrees plus this unknown part. And the angle made here is 90 degrees plus this same unknown part. And so the angle made at B in this triangle and the angle made at B in this triangle agree. So that gives us side angle side congruence for the two blue triangles, which gives us the equal areas of the blue triangles. And now we just need to reason that the areas agree with the areas of these rectangles. So this area is the base of this triangle times its height. Well, 1/2 the base times the height. The height is HJ. So the area of this triangle is 1/2 the area of the rectangle BHJK. This triangle, on the other hand, has a base of IB, BI here, and a height, which is the perpendicular distance from A to that extended line, which agrees with this segment CB. So the base is BI and the height is BC. So this area is half of the area of this square BIFC. So just like we did on the left-hand side, on the right-hand side, we have the area of this square BIFC agrees with the area of the rectangle BHJK. So what? Well, if this square matches in area this rectangle, and this square matches in area this rectangle, then certainly when you put the two areas together, you get the area of this larger square. So A squared plus B squared agrees with C squared. Let's talk about the various merits of this proof, of all three proofs. This proof is due to Euclid, and that means that everyone should learn it as part of their study of geometry. It's a difficult proof, it's difficult to see, but on some theoretical level, it's not a very complicated proof. It simply relies on triangle congruence and the triangle area formula. We don't even have to use triangle similarity in order to get this proof. And so this is, on a theoretical level, it's simple in the tools that it uses. Conceptually, it's very hard for students to identify the congruence between these triangles, especially because they overlap in funny ways. So in high school context, for example, this proof, it has arguable value. It is Euclid's proof, and so it has that going for it, and that's pretty major. Excuse me. But it's difficult for students to grasp the interrelationships between the areas of these triangles, possibly because they have this weird overlap. The pinwheel proof is perhaps the easiest proof to remember if you can remember how to draw the diagram. A lot of students faced with this proof, trying to reproduce this proof, will try to reproduce the diagram and be unable to draw this picture. So long as you can draw this picture, you can basically follow your nose with the area calculations and you will get the answer fairly easily. This makes this a very useful proof to use in the high school context because anybody who can draw the picture should be able to figure out the formulas and draw the conclusion, which is the Pythagorean theorem. On a theoretical level, this proof is not so excellent because in order to make this proof theoretically correct, we need to demonstrate that all of the obvious features of this picture are actually features of this picture. We need to demonstrate that the c by c square can indeed be partitioned exactly in this way, and that all of these lines and seams will line up just so, and that this resulting quadrilateral will be a square, and in order to, and that all of these will be right triangles. It's just to check all of the features that we're actually implicitly assuming about this figure is, on a theoretical level, inconvenient, and that makes this not an excellent proof if we're writing the geometry theoretically. But it is a great proof to teach at the high school level because anybody can do the algebra to check that these two areas are equal. I think as I said, the biggest impediment to teaching this proof is teaching the student to reproduce this diagram. If you're doing that in the high school level, my suggestion is start with the inner square, add these lines for the pinwheel, and then connect the hypotenuses of all four right triangles. Students with that strategy tend to be able then to reproduce the diagram. This proof is both theoretically simple and algebraically simple. And so I would very much favor teaching this proof at the high school level. The only problem with this proof is that it has so many options. Once you reproduce this picture, which is easy to remember and easy to reproduce, there are three similar triangles in this picture, BDC, BCA, and CDA. Among those triangles, there are many, many equations, and I've picked the ones that work best here, and I've performed the algebra that works best and is simplest. If you don't know which equations are the right ones, if you don't know which algebra is the right algebra, then you can really get into the woods here, computing and computing and computing and pushing equations and trying to solve for these terms. So it's it's very simple, but you have to know which paths not to follow, which equations not to write down, which algebra not to perform. And so it's a little bit harder to memorize this proof. But well prepared, this proof really works well at the high school level, especially because it emphasizes similarity of triangles, which is a really important theoretical topic. So I hope this has been a useful overview of three interesting proofs of the Pythagorean theorem. Thank you.